Modern large language models are routinely ingesting and generating context windows approaching 100,000 tokens or more. But as this massive wave of data hits the hardware, the system's processing capability struggles to keep pace, creating a severe bottleneck. The root cause of this strain is a specific hardware mechanism known as the key value, or KV cache. The KV cache acts as the model's working memory during generation. It stores the mathematical context of prior tokens, so the system doesn't have to recalculate earlier steps. As the context window expands, this working memory footprint grows exponentially, quickly eclipsing the memory required for the model's static weights. This chart isolates the problem, comparing static parameter memory against the KV cache as context length increases. Static weights remain flat, while KV cache memory curves aggressively upward. This footprint chokes high bandwidth memory, paralyzing autoregressive generation speeds. To compress this cache, engineers rely on vector quantization. This technique shrinks model data by storing high-dimensional vectors with fewer bits. Legacy vector quantization algorithms face a strict operational trade-off. They either require prohibitively slow offline tuning using second-order Hessian data, making them useless for dynamic inputs, or they operate completely online but suffer from mathematically suboptimal distortion rates. Google Research recently published an algorithm called Turboquant. The researchers claim it can compress the cache to just 3 bits per channel while reducing indexing time to virtually 0. The paper provides a formal proof demonstrating that Turboquant operates near the Shannon information theoretic lower bound, the absolute mathematical limit of data compression. To determine if a 6 times compression ratio actually survives real-world deployment, we have to deconstruct its 2-stage mathematical axioms and confront the strict hardware reality of tensor kurtosis. The primary roadblock for online vector quantization is the need to compress worst-case highly correlated data instantly, without any prior calibration. Turboquant bypasses this requirement by operating data obliviously. It mathematically manipulates the geometric structure of the input data itself. The first mechanical step takes high-dimensional input vectors and multiplies them by a random rotation matrix. This random rotation mathematically forces every coordinate into a predictable beta distribution, regardless of the original input values. In high-dimensional vector spaces, this beta distribution tightly converges into a Gaussian normal distribution. The rotation creates a critical statistical byproduct. The distinct coordinates within the vector become nearly statistically independent from one another. This independence allows the system to abandon the computationally expensive process of multidimensional codebook lookups entirely. Instead of a multidimensional codebook, the system solves a continuous one-dimensional k-means problem. It applies a mathematically optimal 1D scalar quantizer, specifically the Lloyd-Max quantizer, to each independent coordinate. This specific stage of the pipeline produces a quantizer designated as Turboquant MSE, which is optimized purely for minimizing mean-squared error. By inducing statistical independence through random rotation, the algorithm achieves mathematically optimal mean-squared error compression at a drastically reduced computational cost. However, large language models operate under a strict mechanical requirement. The attention mechanism relies entirely on inner products, or dot products, to gauge token relevance, not mean-squared error. This discrepancy reveals a limitation of the first stage. Quantizers optimized purely for mean-squared error do not produce unbiased estimators for inner products. This data visualization compares an unbiased variance histogram with a biased one. At extreme compression rates of 1 or 2 bits, the mean-squared error quantizer skews off-center. This bias degrades the accuracy of the attention mechanism. To correct this, the algorithm employs a 2-stage architecture designated as Turboquant prod. The first step requires the system to intentionally run the MSE quantizer at exactly 1 bit lower than the overall target bit budget. Running 1 bit short leaves a mathematically precise, unquantized byproduct. The flowchart shows the original vector passing through the MSE quantizer and splitting off this remaining data as the residual error vector. The second stage applies the quantized Johnson-Lindenstrauss, or QJL, transform directly to that residual error vector. The QJL transform utilizes a randomized sign matrix to map the complex residual error down to a single bit. The formal proof establishes that adding this 1-bit QJL output back into the primary MSE estimate mathematically cancels out the initial bias. By splitting the quantization into an MSE baseline and a QJL residual correction, Turboquant delivers the unbiased inner product estimations required for LLM attention without bloating the memory footprint. We can now evaluate how this theoretical mathematics translates into academic benchmarks. The researchers validated their claims using the long-context needle-in-a-haystack retrieval benchmark, which tests a model's ability to locate specific information buried inside massive text prompts. The published results report absolute quality neutrality when quantizing down to 3.5 bits per channel. Even at a 4 times compression ratio, Turboquant scores 0.997. This identically matches the uncompressed full-precision baseline model. However, benchmark framing can obscure deployment realities in the highly competitive sector of AI compression research. This split-screen diagram illustrates a recent dispute surrounding a competing algorithm known as RabbitQ. It demonstrates the vulnerability of relying solely on published results. Independent researchers highlighted that the original performance comparisons pitted algorithms running on massive GPU clusters against competitors restricted to single-core CPUs. These inequitable hardware comparisons were presented as straight algorithmic benchmarks. Academic papers only prove mathematical optimality in a vacuum. True architectural viability always requires independent, hardware-level stress testing. That hardware-level validation is exactly what independent developers are doing, testing the Turboquant implementation across Apple Silicon, NVIDIA, and AMD hardware. During these stress tests, developers discovered a critical failure point. Applying the algorithm's symmetric 4-bit quantization breaks the large language model's key tensors. This split-screen visualization shows the root cause of the failure. The left side is a smooth, theoretical, uniform data distribution. The right side shows an actual key tensor in a production model. Key tensors naturally exhibit extreme kurtosis, meaning their data distribution has a highly peaked center with severe, extended heavy tails. The softmax amplification step within the attention mechanism makes the key tensor hypersensitive to these specific heavy tail outliers. Symmetric 4-bit quantization rounds off and destroys those outliers. This causes catastrophic model divergence, driving the perplexity score to over 3,400. To bypass this limitation, practitioners deploy an engineering workaround known as asymmetric tensor quantization. Engineers keep the highly sensitive key tensor at a wider 8-bit precision to preserve the heavy tails. They then aggressively compress the well-behaved value tensor down to 3 or 4 bits using the Turboquant techniques. The resulting impact on hardware is concrete. This asymmetric setup enables a standard 16GB GPU to jump from a 30,000 to 131,000 token context window with lossless inference. Turboquant provides a rigorous framework for approaching the Shannon limit, but achieving extreme compression in deployment requires marrying optimal mathematical theory with the mechanical realities of the tensors themselves.